Hello. So now we consider what assumptions the analysis of variance makes when we conduct such an analysis. Here are the type of data, and you'll remember that the analysis of variance applies where we have a continuous response and yet a categorical predictor. Here we have a one-way analysis of variance in that we've only got one type of thing. Here is fertilizer, albeit at three separate levels, fertilizer A, B and C. You'll remember that implicit within the analysis is a way of partitioning the variability in our data. We looked at the variance as estimated from the variance between the sample means, and then another estimate of the variance in terms of the variance within each of these groups. And by using an F distribution, we can compare formally those two estimates of the variance to see if indeed they differ significantly from one another. It turns out, as you will have been told in that first part, that the sample means are of course unbiased estimators of those population means. What we're actually doing when we are conducting an analysis of variance is in effect fitting a model to our sample data. What does that model look like? Well, it can be variously expressed, but here we have our continuous response, which is yield. And we are acknowledging that there will be some variability, which I'll get onto, this error term. And here we're trying to estimate these things here, the population mean response for yield when plants were treated with fertilizer A, B or C. And implicit in our analysis is that around these overall effects we have normally distributed variability, and that variability has a mean of 0 around the population level effect and a fixed variance. So independent of what level of fertilizer we have, the variability is assumed to be the same. The null hypothesis is that the population mean responses to these fertilizers A, B and C are all precisely the same. The alternative being that somewhere there is a difference in the yield according to one or more of the fertilizers. Let's have a look at the meaning of this term error. Here is our data, and here are the sample means, which are our very best estimate that we have of the population means. Here is the error in this data here, sometimes called a residual. Of course, this is our very best estimate, but it may not be the true value of the population mean, but it's all we've got to go on. Now, the first point I'd like to make is that the error is an inadequacy of the model. It's not your inadequacy. So it's not me, it's you. It's the model's fault that it simply can't explain all of the variability in the data. It's not a mistake, it's just the bit that's left over when we fit our model. Now, just to emphasize, typically when we fit analyses of variance models, we assume that that error is normally distributed around any given level of the treatment. So here we're assuming a normal distribution of residuals. We're also assuming homogeneous variance across each of these groups, i.e. the variability is not higher in one group or another. Why are we making that assumption? Well, it boils down to our use of the F distribution. You remember the F distribution is a ratio of two estimates of the variance, but each of them are assumed to have been drawn from either the same normally distributed population or two different normally distributed populations with the same variance. So the normal distribution assumption comes directly from our use of the F distribution. Let's review what assumptions we're actually fitting. I've called it a general linear model, but in fact it applies to analysis of variance, of course, as we've got here, but also other forms of general linear model like linear regression, multiple regression, analysis of covariance, and so on that you'll meet later. The first key assumption is independence, that, for example, we are not measuring the same individual subjects many times and treating them as independent data. That's, of course, a key assumption. And we've seen this one, the homogeneity of the error variance and also the normality of the error. How do we test for these? Well, in the RStudio part, the practice part of the analysis of variance, you'll see how we can extract residuals and simply plot out what our variance looks like around each of the fitted models and also assess normality. And the final assumption is one, effectively, that we have chosen the right model to represent the population level process. And it boils down to the right sort of assumptions in terms of the structure of the population model that we have fitted. What do we do if those assumptions appear violated? For example, our residuals do not appear nicely homogeneous amongst the groups that we are comparing. The first thing is to keep calm. This happens regularly, and we as biologists have a whole range of tools available to us to deal with it. The most common way of dealing with it is to consider a transformation of the response. So, for example, if the residuals tend to get higher, for example, if we're doing a linear regression and they get higher with the level of the predicted response, then typically a log or square root works wonders. However, the reverse, where we often take the response to a squared or even higher power, can help to homogenize decreasing variance as it decreases with increasing predicted values. So we can think about transforming our response, and there's nothing wrong with that. 2 bananas is equal to 4 half bananas. We can apply statistics to the most appropriate way of measuring our response variable. If we have a relatively simple design and no transformation can be found to ensure that the assumptions are reasonably valid, then we can consider a non-parametric test, which doesn't make the assumptions of normality and homogeneity. It does, of course, make many other assumptions, but they are not part of them. Thank you for listening to this R-Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.